So the rest of this chapter is really going to be focused on, or the rest of this lecture really is going to be focused on muscle mechanics, kind of how muscles work in general. Not specifically what each muscle does, but generally just how muscles kind of all together work in the body. So there are a couple of things that contribute to how kind of forcefully and how fast muscles can contract. Some of that is from chapter 9. So we talked about load and recruitment in chapter 9, right? If you have a heavier load, that's going to be a slower contraction. If you have more recruitment, more muscles involved, that's going to be faster, you can hold it longer, etc., etc. And then also those different fiber types, right? Slow oxidative, fast oxidative, fast glycolytic. Those things all contribute to kind of how strong and how fast muscles are. But then there are a couple other things here in chapter 10, specifically what we call the arrangement of the fascicles, i.e. kind of how the fascicles that are kind of shaped into the muscle, and then lever systems. And that is where we're going to head here with the rest of this little lecture. So all skeletal muscles, of course, have fascicles, right? Skeletal muscles that get bundled together into fascicles, fascicles then get bundled into a whole muscle. But the arrangements of those fascicles can vary. And so we end up with muscles not only that have different shapes, but then those shapes affect their functional capabilities. We have kind of 4 common patterns, what we call circular muscles, convergent muscles, parallel muscles, and pennate muscles. In some of them in the name, they kind of tell you what they are going to be shaped into. So for instance, circular muscles are, of course, well, circular, right? They're round. They're concentric rings of muscle tissue. Convergent muscles are going to converge, right? So they have these really, really broad origins that tend to kind of narrow towards a single tendon insertion. And so the pectoralis major muscle here is a very good example of a convergent muscle. Parallel muscles are muscles that have long, parallel muscle fibers, typically in a very strap-like fashion, like the sartorius here. Then we have muscles that are known as fusiform muscles. These remind me of rail spindles. So they're fat in the middle. The fibers are running in parallel a direction to each other, and then two origins appear, insertion down here. Then we have pennate muscles. Now, pennate muscles have very, very short fascicles. You can see very, very short fascicles that then attach at an angle to a central tendon that runs the length of the muscle. They can be either unipennate, meaning kind of attached only to one side, bipennate, meaning attached to both sides, on both sides of the single kind of central tendon, or you can even have multi-pennate muscles, where you've got kind of multiple attachments, almost like feathers, that will insert into a single tendon then. And so these different shapes of these different muscles will affect kind of their range of motion, i.e. kind of what is the amount of movement can they do, and then their power, their strength. So the range of motion depends on the length of the fibers. If you have a longer fiber, it can do more shortening and thus give you a greater range of motion. Power depends on the number of muscle fibers, right? If you can get more fibers, then you can get more power. So muscles that have a good range of motion are generally less powerful than muscles that have more power but generally a smaller range of motion. So for example, the parallel and fusiform muscles, they're longer, so they've got really good range of motion, but they don't have as many fibers, so they're not as strong. Whereas the bipennate and multipennate muscles, their fibers are shorter, so they don't have as good a range of motion, but they've got more of them, and so they're more powerful. And our body is really kind of a mix of all of these different types of muscles. Now, the last thing here that we're going to discuss is leverage, right? In order for our muscles to work, they have to have something to pull on. And that is our skeleton system. So there are 3 components to a lever system. There's the lever itself, which is the rigid kind of bar that moves on some fixed point called a fulcrum. So in the body, the rigid bar is the bone, and the fulcrum, the hinge point, is our joints. The effort is then the force, which we get from our muscle contractions, that is applied then to the lever in order to move some sort of load or resistance. Now, load is what we're moving, but we're not just talking about whatever it is maybe that we're trying to carry, but it's also all of the weight of the bones and the tissues itself. That's part of the load that we have to take into account when we think about how our muscles function. So what levers allow us to do is to move heavier loads or move loads further or faster, right? So there's a really famous quote by Archimedes: "Give me a place to stand and a lever long enough, and I will move the world." And that is essentially what our lever systems in our body allow us to do. They allow us to do things that we wouldn't otherwise be able to do if we didn't have the lever systems. So let me give you 2 kind of real-world examples here in just a second. There are 2 types of levers. Levers that are called power levers, ones that have what we call a mechanical advantage, or speed levers, which means they have a mechanical disadvantage. So in power levers, the load is really close to the fulcrum. The effort is applied farther from the pivot point, and what results from this is that you can use a really tiny effort and still move a large load. So power levers they tend to be slower, but they're more stable, and they're much more often used when we're looking for strength. Now, speed levers, the load is further from the fulcrum. The effort is applied close to the fulcrum, and the result is that we can move a load really rapidly over a really large distance. So speed levers, not as much force, but we get a greater range of motion, and we get greater speed, hence speed levers. So again, how about some real-world examples, right? So here is a power lever with a mechanical advantage, right? So the load is really close to the fulcrum. The effort is applied further away from the fulcrum. So here's this gentleman here. He can apply a fairly little effort in order to lift the load of the rock. Now, conversely, speed levers, the load is further away from the fulcrum. The effort is applied fairly close to the fulcrum, and so we lose some force, but we gain a lot of speed. And so in this instance, the person jumps down, and the acrobat's going to fly up in the air and go at really quite a high speed. In fact, actually, it's funny that this is what we're talking about right now, because I just watched a video the other day on America's Funniest Videos, which is just not a show that I usually watch, but I happened to watch it the other day, and somebody jumped on like a raft out in the middle of a lake, and the next thing you know, like the other person on the other side of the raft just went flying off like high into the air and ended up in the lake. It was pretty darn funny, actually. So power levers, small effort moves large load. Speed levers, we lose a little power, but we can move loads pretty far and pretty fast. So based on the position of the effort, the fulcrum, and the load, we have 3 classes of levers. First class levers, second class levers, and third class levers. First class levers, the fulcrum is kind of situated between the load and the effort. So scissors are a really good example of that, or a seesaw, right? So we apply the effort here, the load is here, So we can apply a little bit of effort and we're able to move the load. So a really good example in the body is the muscles that allow you to kind of raise your head. So the fulcrum here is, of course, this pivot joint here, or the glenooccipital joint, excuse me. So we've got a little condylar joint here, that's our fulcrum. The effort is the sternocleidomastoid muscle, and the load is essentially the weight of the head. So the effort is applied that moves the load against the fulcrum, and that is a first-class lever. Second-class levers are what you have been using anytime you have ever used a wheelbarrow. So these muscles tend to have a mechanical advantage. So for looking for really strong movements, but generally really small movements. In this instance, the load is between the fulcrum and the effort, right? So in the wheelbarrow example, the fulcrum is the wheel, the load is whatever it is that you're trying to haul around in your wheelbarrow, and your effort is here at the end of the wheelbarrow. And if you've ever put too much in your wheelbarrow, that's me, you'll know that even with the greatest lever ever, you're still not moving it. In the body, a really good example is what we do when we plantar flex and stand up on our tippy toes. So here in this instance, the fulcrum is the joints in the ball of the foot. The weight of the body is all of the load, and then the effort is here supplied by some of our calf muscles here in the back. That allows us to lift the load on this that's between our effort and the fulcrum. So that's a second-class lever. And then the most common type of lever that we have in the body and that most of our muscles operate under are third-class levers. In this instance, the effort is applied between the load and the fulcrum. If you've ever used tweezers or forceps, that is an example of a third-class lever. So here's the fulcrum, you apply the effort here, and then you're able to kind of pick up your object and move your load. These muscles tend to be at a mechanical disadvantage, so really large movements, really fast movements. So a good example in the body is the biceps brachii. So here is the fulcrum, that's our elbow. The biceps brachii contracting is our effort, and there is the load of the, say, weight that we're trying to lift in order to lift some weights and work out our muscles a little bit. So first class, second class, third class levers. So in terms of what I will expect you to know for lecture, it's the functional groups, how muscles work, how muscles are named, and some of the basics of muscle mechanics that we just went over, how fascicle arrangements affect speed and power, and the principles of leverage. Now for lab, you'll have to be able to tell me what the muscle looks like, so you'll need to be able to ID it in a picture, on a diagram, on a muscle model, etc., etc. All of the attachment points, origins and insertions, the primary action of the muscle, like what does the muscle do, and kind of what its antagonist or synergist, kind of that kind of functional group type classification may be. The best way to tackle muscles is to tackle them in small pieces. So look at head and neck muscles, then look at your trunk muscles, and I would look at your trunk muscles in sections as well. You can look at your breathing and your postural muscles that we find in the thorax, the muscles of the abdominal wall, the shoulder muscles that are going to act on the arm, and then the pelvic muscles that are going to act on the thigh. And then when you look at the upper limb, you can look at the arm muscles that act on the forearm muscles that then act on the wrist and hand. And then when you look at the lower limb, the thigh muscles that act on the leg, and the leg muscles that act on the ankle and foot. I would not at any point try to learn it all at once. I would do section by section by section, because if you did it all at once, it looks kind of like that. And you're like, oh my God, it's too many muscles. But if we look at, let's say, just the head muscles, we're looking at 5 or 6 or maybe 7, 8 muscles, depending on how many is on that list in lab. If we're looking at just the thigh muscles, we're looking at much smaller groups of muscles. Or you could also even not only break it down kind of by region of the body, you can break it down by anterior and posterior. So just look at let me go back here for a second. So let's just look at the posterior trunk muscles, then go back and look at the anterior trunk muscles, or whatever the case may be, but just break it into pieces, because it's much more conquerable when you break it into pieces like that.